My plan for today is cover a lot of the basic like expected utilities slash insurance problems that you're going to be finding on your midterms. Uh, just because I know that last lecture was pretty heavy on the conceptual side, not a lot of application. So I just want to get you guys exposed to those problems and see that they're really not as hard as maybe um, you kind of would think they are. Um, and if I have enough time, I'm going to go ahead and get started on explaining price elasticity or just general elasticity. Um, just because we're going to go ahead and get started on the extra problem set 6. So that's my goal for today, and we're going to see if we're going to be able to do that. So with that being said, if you guys want to just kind of work along with me, you guys can pull up extra problem set 5. And we're going to start working on some of the problems towards the second half of that. So go ahead and get that pulled up, and I'll pull it up with you guys as well. So we're going to start with question 7. Okay. And this one actually is very tricky. I had to kind of look it over a few times in order to actually understand what was going on. But I think that as we work through this, once you kind of see what is going on and like what the wording actually means, it becomes a little bit easier to understand. So with that being said, if everybody is already there and pulled up to question 7, I'm going to go ahead and get started. So we have that, actually let's just write this. Oops. This is extra problem set 5, question 7, and we have Diego has $6,400, and he's going to bet on a soccer game. So the idea of betting on some sort of uncertain event is going to be like an indication that we're working with either an expected utility question, or you can think of it as, I guess, insurance, right? But in this scenario, because the result of the soccer game is uncertain, right, we're going to treat it as an expected utility kind of question, right? So team A is a favorite to win. And so as a result, you guys can kind of think of 80 cents per ticket as being like the cost of the insurance, right? So you will pay 80 cents per ticket for $1 of reward. And for each amount of tickets, or for each ticket that you buy, if that team wins, right, then you're going to get the payoff of 1 times however many tickets you bought. Okay, so that's kind of the intuition there. And so because the tickets for team A, right, are more expensive, that reveals that the probability that team A wins is higher than the probability that team B wins, right? And that's also explained in words, but that's just kind of some intuition to kind of go along with what the word, with what the words say. So the price of tickets A are equal to 0.8, and the price of tickets B are equal to 0.2. Okay, so what we have to do is come up with a utility function that kind of represents what his preferences are, right? So we know that his utility function is going to be based on whatever income or consumption he's going to be able to buy. So that's going to be the money that the tickets bring back to him, right? So we have it that his utility function, right, is going to be some sort of expected utility, right? So his expected utility, right, is equal to 0.5, right? And so the reason why I have a 0.5 that's right there is because if you read in the prompt, Diego believes that the 2 teams are equally likely to win, right? Which kind of explains why we have this 0.5 right here is because he believes that each outcome is equally likely. Okay, so that's why his utility is formed in this way. We also have it that the expected value of his wealth is going to be in the form of a natural log. So if you remember what I said in last lecture, if someone has the natural log or any sort of diminishing returns kind of utility function, then they're going to be risk averse. Okay, so we have 0.5 times the natural log, right, of however many tickets you bought. So TA in this case is used to represent the amount of tickets for team A that he buys at 80 cents per, right? And the reason why you can just substitute TA is because each ticket is worth $1. So if he has 500 tickets, for example, that's equivalent to saying $500. So you can kind of just use that as a placeholder for now. So this is going to be one part of it. And we know that these probabilities have to equal to each other, or have to sum up to 1, is what I should say. And so we get that this is 0.5 times the natural log of TB. And is anybody confused so far about like what the setup? I think once you're able to achieve the setup, the rest of the question is a little bit more straightforward. But are there any questions about how I set up the question so far?
Yeah.
Yeah.
With the 0.5s, is that because the ticket price moved to 50 cents afterwards?
So that's not because of that, right? It's because of the fact that inside the prompts, it says that Diego believes that each team is equally likely to win, right? So you know that utility is based on preferences, right? Not what actually, well, so the preferences are based on what actually is existing, right, inside the prompts. But regardless of what the actual probabilities of each team winning are, we know that he believes that there's a 50-50 chance that either team will win. And so that's why we have to set up this 0.5 instead of say 0.8 or 0.2. And I think that's probably one of the trickier aspects of setting up this problem is coming up with these probabilities right here. All right.
So if they'd said like they think team A is twice as likely to win, then would it be what, 0.75 to 0.25, or like how would you set that up?
Well, if he were to say, like, if Diego thinks that team A is twice as likely, right? Well, then this would be 0.67, or it would be just be 2/3, and this would be 1/3.
Okay, yeah,
right?
That makes sense. Gotcha.
Okay. So the thing is that he thinks they're equally likely to win. So we use 0.5 and 0.5. Okay.
Perfect. Thank you.
So let's take a look at how many tickets Diego will buy, given that this is his utility function, and given that these are the prices of each ticket. So you notice that what we can actually do is find an MRS, right? That is going to be the marginal utility of TA over the marginal utility of, I don't know why I have 1 right here, of TB. Okay. And so this is actually a really unique problem because I can almost guarantee you that most of the time you won't need to set something like this up. But what I like about this problem is that it encapsulates expected utility, and it also encapsulates the buying and selling, which is what we're going to see. Okay, so the marginal utility of TA, right, we're going to ignore this part, is just going to be equal to 0.5 over TA, right? So that's the derivative of the natural log, it's just 1 over. And so we also get 0.5 over TB right here, right? And this whole equality is equal to 0.5 TA, or over TA, times TB over 0.5, right? These 0.5s are going to cancel out, and we're going to get that this is equal to TB over TA, right? And so we check that we have diminishing marginal rate of substitution, and we see that because we have TA as our like x-axis, that we do have diminishing marginal rate of substitution. okay? And just to kind of tie back, this should make sense because of the fact that we have a natural log function, right? Which implies that this person is risk averse, which implies that they prefer to have kind of an equal amount of each scenario, right? If that makes sense. Okay, so this is our MRS, and we're going to set this equal to our price ratio, which is PA over PB, which is going to be equal to 0.8 over 0.2, which is equal to 4, right? And so from here, we have that TB at the optimal point, right, is going to be equal to 4 times TA, right? Meaning that at the optimal point, there's going to be 4 times as many tickets for Team B as there are for tickets of Team A, right? And that's because he thinks they're equally likely to win, and basically the price for ticket B is cheaper, okay? So he'll want 4 times as many tickets for Team B because they're cheaper and he thinks they have an equal chance of winning, okay? So let's hold on to this, right? And let's erase some stuff. So let's actually just erase this bottom part, okay? From here, we can actually just plug this into our budget constraint. So we have that 6,400, which is, remember, our wealth. That's not coming up well. So 6,400 is equal to PA. So PA times TA plus PB times TB is equal to 0.8 times TA plus 0.2 times TB, but we know that TB is really just 4 TA, right? And so this whole thing is going to be equal to 0.8, and so we'll get that 6,400 is equal to 1.6 TA, right? And so if we divide 6,400 by 1.6, so 6,400 right here, and let's just go ahead and use our calculators. So 6,400 divided by 1.6, that's going to be equal to 4,000, right? So TA is equal to 4,000, right? And so because TA is equal to 4,000, that tells us that TB is going to be equal to 4 times that amount, which is going to be equal to 16,000, okay? And so that's going to be the optimal amount, right, given the current circumstances, okay? But we're also given some more information at the end, which says that because one of the key players gets hurt, the probabilities get affected, and so these ticket prices are still going to are going to be affected as well, right? We don't have any change in what Diego thinks, like none of that's given inside the prompts. So we're just going to assume that he still believes that each team is equally likely to win, right? So this utility function is going to stay the same, meaning that our MRS is also going to stay the same, all right? Does everybody kind of see what I mean by that? All right. If you do, if you have any confusions, either speak up or leave it in the chat and I'll try to get to that. But essentially what I'm saying is that nothing about Diego's preferences changes, right? Which means that our MRS, which is based on preferences, is also going to stay the same, all right? The only thing that changes here is the price of the tickets, okay? So we're given that he buys some new tickets and sells some of his old ones. So this is like a perfect example of buying and selling, where we see what this value is in terms of income. So we want to see what his new income is pretty much what I'm trying to say. So we have that PA star is equal to 0.5, and that PB star is equal to 0.5 as well, okay? So as a result, we want to see how much are these tickets worth, okay? we have that if you sell all of your tickets that say Team A is going to win, you would get 2,000. So you would get $2,000, right? That's just selling 4,000 tickets for 50 cents each. And if you sold your Team B tickets, right, that's just 16,000 tickets for 50 cents each. And that gives you 8,000, which in total gives you 10,000, right? So your new income is 10,000, which if you notice, right, is going to be higher than the 6,400 that we had beforehand, okay? So let's erase some of this stuff right here. We have, this is equal to TB over TA, right? This is something that we already found in the previous part. So we essentially have to find a way of distributing our $10,000 equally, right? When we have that the tickets are 50 cents each, and he believes that each team is equally likely to win, okay? So we have it that TB over TA, which is our MRS, can be set, and let's erase this. We no longer need this information, right? We set TB over TA equal to our new price ratio, which is 0.5 over 0.5, right? And so we get that TB is equal to TA at the optimal point, right? And so kind of like we did for the previous part, we're gonna put this into our budget constraint, and we're gonna get that 10,000 is equal to 0.5 TA plus 0.5. We know that TB is equal to TA, so we can just plug that in right here. And we get that this is just equal to TA, right? And so because we know TA is equal to TB, we can also say this. So, right, basically, Diego is going to, after the price changes for tickets, right, he's going to purchase 10,000 tickets for Team A and 10,000 tickets for Team B. And so because we have it that Team A wins, each of those tickets has a payout of $1, meaning that his wealth at the end is equal to 10,000. All right. Are there any questions about that? All right. I don't see anything in the chat. So I'm going to assume that
Hi.
you guys kind of understood that, but definitely feel free to stop me if I'm wrong about that.
I had a quick question.
Yeah, what's up?
Can you like explain again why we're using like the natural log for the utility function?
So yeah, I think that for you guys, and just I mean for me as well, finding this expected utility equation was the hardest part, right? So first off, we know that we're going to be using some sort of expected utility because we're dealing with uncertain events, right? We can't have Team A and Team B win, right? It's either one of the two, okay? And we know that Diego thinks that each of the teams has an equal chance of winning, which is why we assign 0.5 in front of each of these, right? But we want to see, right, how, like, when it comes to expected utility, and I don't know how much of like a math background you guys have, right? But expected utility is like x times f of x, right? So the value of x, which is 0.5, times f of x. This is a very similar process in that essentially this is like the value of x, and this is like your f of x, where this is a function, right, of the utility that you get when TA, right, is the amount of tickets that you have, right? So this natural log is a function of his wealth, right? Which is why we plug this into the expected utility equation, because it captures how he values his wealth, if that makes sense, right? Where each unit of like each dollar provides him the natural log of that dollar's worth of utility. Does that make sense? I know that's kind of tricky to kind of think about.
So where did you get the 10,000 from?
Well, 10,000, right? So first off, we know that after he sells his tickets, that his new income is $10,000, right? Correct? Do you understand?
I don't
that?
see that on the question.
Huh?
I don't see that on the question.
So we have it inside the prompt. So this is right. We have it in the prompt that after he buys the optimal amount of tickets, given that they were 80 cents and 20 cents respectively, right? He goes back to like whatever market and he sells some of those for these new prices. So he previously had 4,000 tickets for Team A winning, and that produced $2,000 for him. And he also had 16,000 tickets for Team B winning, which produced $8,000 for him. And so you add those two up and you get $10,000, right? And so that's the amount of income that he has. But that doesn't quite cover why we have 10,000 as our final answer. The reason why is because we know that his MRS is TB over TA, right? And we know that the new price ratio is 0.5 over 0.5, which is just 1. And so we know that at the optimal point where the MRS is equal to the price ratio, that TB is going to be equal to TA, right? There's going to be equal amounts of tickets for Team B winning as tickets for Team A winning, okay? And so when you plug this back into the budget constraint, we get that 10,000, which is his new income, is equal to 0.5, right? And I guess this should be the natural log. Or actually, no, this is the budget constraint, so it doesn't really matter. So this is the 0.5, so that's the cost of each ticket, times the amount of tickets that he buys for Team A, plus the price of ticket B. And this is actually supposed to be TB, but because we know that the amount of tickets for Team B is going to be equal to the amount of tickets for Team A, we substitute that in here so that we can be working with the same variable, right? And so we get that this whole thing is just equal to TA, right? 0.5 TA plus 0.5 TA is just equal to 1 TA. And so we get that 10,000 is going to be equal to the amount of tickets for Team A that he purchases, which because of this is also equal to the amount of tickets for Team B that he purchases, all right? So at this point, he has 10,000 tickets for each team winning. And when Team A eventually wins, we have it that the amount of tickets for Team A that he had was 10,000, which each ticket has a payoff of $1, which means that his wealth is 10,000 times 1, which is just 10,000. Does that make sense?
Yeah, thank you.
Does that mean that if either team won, he would have gotten 10,000?
Yeah, if either team had won, he would have gotten 10,000.
Damn, I bet with this guy.
Yeah, this guy's got a nice setup. Are there any other questions about this particular setup? I think this is the hardest problem in the problem set, and I think it's actually one of the harder questions within all the problem sets. So it's okay to be a little bit confused, but hopefully it's all kind of coming together and you can understand how we mix new material with old material, right? Okay, I'm gonna take it that there's no more questions and move on. We're gonna go on to question 8, okay? So question 8 is more in line with the kind of question that I would expect you guys to see, right? Where it's pretty straightforward what the setup should be once you know how to kind of work through these. So we have that this person, which is a football player, has a utility function that's equal to the square root of consumption, right? So we know that this person has diminishing returns, which means they're risk averse, okay? Whether we need to use that for the problem or not is to be determined, but that's kind of what we know already about this person, all right? So we have that if he's not injured, he will receive an income of 16 million. And if he's injured, he will receive an income of 10,000. So right off the bat, we know that the probability, or basically we know that the bad state is him getting injured and the good state is him not getting injured. And so the probability of being in the bad state, right, being injured, is equal to 0.1, which means that the probability of nothing happening, being in the good state, is equal to 0.9, right? And so we want to know what his expected utility is, right? So we know that the formula for expected utility is equal to probability of the bad state times utility consumption in the bad state, right? Plus probability of the good state times your utility of consumption in the good state, okay? And I forgot who asked the question. I think it was maybe Ryan. This is kind of why we had the natural log set up in our previous expected utility, right? Which is the same reason why we're gonna have the square root of consumption in this expected utility, right? We're just seeing what the utility would be in the bad state, right? And so let's just go ahead and kind of fill in these numbers, and we might be able to get a better explanation. So we know that this is equal to 0.1, and his utility in the bad state is going to be a function of how much he can consume in the bad state. So his utility when he gets injured is going to be a function of how much money he gets when he's injured, right? And we know that his utility is equal to the square root of how much he gets when he's injured, right? And so we're going to fill in that step. We're going to fill in this part in the next step, okay? So 0.9 is the probability that he doesn't get hurt. And this is also, right, the utility that he gets when nothing happens, which is going to be a function of how much money he gets, which is equal to, right, the square root of consumption in the good state. So we were already given that consumption in the bad state is 10,000, and that consumption in the good state is 16 million. Okay, so basically we know that if he were to get injured, which has a 10% probability of occurring, he's going to receive $10,000, and his utility with that $10,000 is the square root of 10,000, okay? So this is equal to 0.1 square root of 10,000 plus 0.9 square root 16 million, right? I'm just gonna leave it at that. And I would just welcome you guys to just use a calculator because it's better to be safe than sorry. So we have that his utility with $10,000 is equal to 100, okay? So this is equal to equal to 0.1 times 100 plus 0.9, and you want to find the utility that he gets with 16 million, which is equal to 4,000. All right, and when you add these up, you get that 0.1 times 100 is 10, plus 0.9 times 4,000 is just 3,600. All right, and so we get that his expected utility is 3,610. Okay, which is going to be answer choice A. Are there any questions about that problem in particular? Hopefully you guys are kind of seeing what the general setup should look like, right? We plug in the probabilities of each event occurring, and we multiply each of those probabilities with the utility that they would get in that given state of the world, right? either the
That
good
makes
state or the
sense.
bad state.
I have a question real quick.
Yeah, what's up?
So how is it that that his income is called C? Why isn't it called M?
Um, well, we just assume that whatever income he gets is going to be how much he consumes.
Oh, okay. So it's not like he's receiving income separately. It's like whatever he gets is money that he can use in the future, so we call it consumption.
Yeah, exactly. And we just say that the price is one. So M is equal to C, right?
Okay.
In that
Thank you.
case. All right. Are there any other questions about this problem? Um, I'm hoping that you guys are starting to get a little bit more familiar with what you're expected to be able to do, right? Um, Hopefully, after you do enough of these problems, this becomes a very easy setup. And like the math itself isn't very complicated at all. Um, it's definitely the setup that's the hardest. Okay. So we're going to move on and do question 9. I think this one can be a little bit tricky as well. All right. Also, I want to make an announcement before I forget that I will be doing the full week's worth of like CLAS stuff next week, except for Thursday. So normally I wouldn't do stuff on Wednesday if it was in person, but because it's just remote, I can do it whenever. So I'm going to do my Monday and my Wednesday groups so that you guys can get as many practice problems as possible. And I'll still have Tuesday drop an hour. So just to kind of throw that out there before I forget to say. All right. So question 9 is we have a utility function or an expected utility function that's going to be equal to 0.5, the natural log of y no rain, right? So y is his amount of income, and this is given the condition that there's no rain. So plus 0.5, the natural log of his income when there is rain, right? So there's a 50-50 chance that there's going to be rain or no rain. And so that's what the probabilities here are used to represent. And this is his utility from the income that he gets, okay, in those given conditions. So we have to see which crop he'll plant. And so the way that we do that is we just compare which expected utility is going to be higher, all right? So let's just do wheat first, right? His expected utility is going to be 0.5 times the natural log, right, of no rain, so 28,000, plus 0.5 the natural log of his income when there is rain, which is 10,000, right? And so you're for sure going to need a calculator on this. I doubt you would get something like this. Actually, I don't know. There used to be a no calculator policy, but with it being remote, I mean, I don't know. How can they know if you use a calculator? So basically, we're just going to figure out what the expected utility is here. So natural log of 28,000 times 0.5. All right, and so you get this really weird like decimal. So you get 9.725, right? And I've already done this problem, so I know that the significant figures are important. But if you store it in your calculator, it doesn't really matter. You can always just reference it. But this is the expected utility from planting wheat, okay? And so we want to compare that to the expected utility from planting, I don't know why I said crop. This should be corn, right? From planting corn, okay? The expected utility in that case would be 0.5 times the natural log, right, of 19,000 because that's the income when there's no rain from growing corn, plus 0.5 times the natural log of 15,000, right? And again, you would basically just figure out what that is. So let's do that. All right, and you get that this is equal to 9.734, right? So these numbers are really close, right? But what you notice is that the expected utility from planting corn is higher than planting wheat. So this individual should plant corn, right? Instead of planting wheat. But we get a part B where we're saying, what if this farmer has the option to choose to plant his field with half of each crop, right? So this is part A. Actually, let's erase this. In part A, we got that corn had expected utility equal to 9.734, right? And so in order to decide whether he should plant his field with half and half, we have to get an expected utility that's going to be higher than this number right here, okay? So how we figure that out is, here we go. The probability of each event, this is really, the probability of each event, like rain or no rain, is still going to be 50-50, so that doesn't change. The natural log function, right, that's how he values, that's how he gets utility from each dollar of income that he gets, right? That's not going to stay, that's going to stay the same, right? Plus 0.5 natural log YR, okay? What's going to change is going to be YNR and YR, right? So if he goes half and half, we're going to have it that YNR is going to be equal to 28,000 over 2 plus 19,000 over 2, right? Meaning that half his crop is wheat and half his crop is corn, right? So that equals out to, let's see, 28,000 plus 19,000 divided by 2. This is 23,500, right? And we want to find what YR is, right? This will be a very similar process, except we do 10,000 over 2 plus 15,000 over 2. That's going to be 25,000 over 2, which is just 12,500. Okay? And so we plug these values into our expected utility equation, right? So we get 0.5 times the natural log of 23,500 plus 0.5 times the natural log of 12,500. And we get that this is equal to 9.749, right? And if we compare that to the expected utility of only planting corn, right, we get that going half and half actually produces a higher expected utility, right? Which is why the farmer should plant it half and half, right? Are there any questions about this one? All right. Okay. I'm gonna take it that you guys are getting a little bit more comfortable, right? That's kind of the hope, is that with each question, you guys are getting more and more comfortable. Hopefully every step of this made sense. And if not, you guys can always reference the recorded lectures that I post. But yeah, that's question 9 for you guys. Let's see how many we can get in 10 minutes. So we have question 10 coming up. Right, so here's question 10. Right, we basically have that there's a 50% chance that all eggs carried on any one trip will be broken during the trip. So he can either bring 12 or bring 6 at a time. And so they want us to show like what all of the possible outcomes from each strategy is. So let's just show the outcomes. So strategy 1. is 12 eggs at a time. And so the outcomes from this strategy are 12 eggs broken or 12 eggs unbroken, right? And there's a 50-50 chance of this occurring. So basically, the expected value is equal to 0.5 times 0 plus 0.5 times 12, which is equal to 6, okay? And so let's go to strategy 2 and see what all of those outcomes are, okay? So this strategy is when you bring 6 eggs at a time, right? So there's gonna be 2 separate trips. All right, 6 eggs at a time. So the outcomes, right, there's gonna be more outcomes because there's more trips in this case. So we get that outcome 1 is that there's 6 eggs broken plus another 6 eggs broken, right? Which means that in trip 1, all of the eggs broke, and in trip 2, all of the eggs broke, okay? So outcome 2 is that 6 eggs broken plus 0 eggs broken, right? And I think that you guys can kind of see the pattern. So I'm just going to, without saying it out loud, I'm just going to keep writing it. Okay, and what's important to note is that there's a 50% chance of this occurring, and there's a 50% chance of this occurring, right? So this is 50% and 50%. But, right, with this probability here, there was a 50% chance that 6 eggs were broken, and then there was also a 50% chance that on trip 2, 6 eggs were broken. So this is equal to 50% times 50%, right, which is equal to 25%. Right, and this is true for all the way down from outcome 1 to outcome 4. So if we were to set up an expected value, right, for this strategy 2, and we're just gonna erase this so far, right, just for now. So we get that the expected value is equal to 0.25 times the outcome, and so that's 0 eggs plus 0.25 times the outcome, which is 6 eggs, plus 0.25 times the outcome, which is 6 eggs, plus 0.25 times the outcome, which is 12 eggs, right? And if you find what this is equal to, right, this is 1.5 plus 1.5 is 3, and this is 3, so this is equal to 6, right? And you see that the expected value, meaning that the expected, or I guess expected outcome, is that you're going to return back with 6 eggs, right? So basically, if you were to keep going on trips, right? If you had infinite attempts of bringing 12 eggs home, right? That on average you would come home with 6 eggs. So that's kind of what it means. So the expected outcome is 6 eggs for each case, which is equal. The part B of this question is, what is the key difference between the 2 strategies? I wouldn't expect you guys to really know this unless you guys have taken stats classes, but essentially by having more outcomes, that reduces the variance of each event. But that's kind of all it really means. So part B would say that you have less variance, but I don't think you guys would really be expected to know that in an econ class, all right? But I think what you would be expected to show is that in each strategy, the expected outcome is 6 eggs, okay? So let's go to question 11, or actually let's go to question 12 because I know that 12 is a kind of a good one. So let's do that. And then if we can get to 11, we'll get to 11. All right. So question 12 is a good one. And it's not the pirate ship, but it's like a ship question. So the ship is worth $200 million. So basically, if you guys remember in my lecture on Monday, I said that if you had a car that was worth $500, then the maximum amount that you can lose on that car is 500, right? So the ship being worth 200 million means that L is equal to 200 million. Okay? Yeah, and so if the ship sinks, then he loses all of that 200 million, right? Which is kind of just showing this. The probability that it sinks is equal to 0.02. And his total wealth, including the value of the ship, is 225 million, right? So M is equal to 225 million, right? And his expected utility is equal to the square root of his wealth. And so what is the maximum amount that William would be willing to pay in order to be fully assured and get against the risk of losing his ship? So this is one of those situations where you're basically going to see how much does the cost of insurance have to be in order for him to be indifferent between having full insurance and having no insurance, right? So that's kind of in words, it probably doesn't resonate much with you guys. So that's why we kind of have to work through this problem and see exactly what I mean by that. So in order for you to be indifferent between having no insurance and having full insurance, the expected utilities would have to be the same, right? So we want to find the expected utility with no insurance. That way we can see how much utility you get from that, okay? So the expected utility with no insurance is equal to probability of the bad state times the utility of his consumption in the bad state plus the probability that no accident occurs, or I guess this is good, times the utility that he gets when nothing bad occurs, right? So his utility when he doesn't get in an accident. So we know that this probability right here is 0.02, and we know that the utility is equal to the square root of his wealth, or I guess consumption. Those are kind of interchangeable terms. So in the case, right, where he does get in an accident, we know that his consumption is going to be equal to M minus L, right? If you remember from Monday's lecture, this is consumption in the bad state with no insurance, okay? So that's all it really is. And so we have that this right here, this probability is equal to 0.98, and this is equal to the square root of just M, right? Because if nothing happens and he doesn't have to pay anything to the insurance company, then what he has is just what he started off with, okay? So we get that this is equal to 0.02 times the square root of 25. So I'm just going to be working, I'm going to take away the million so that I don't have to have like long kind of attachments to this, like all the zeros. And then I'm just going to add a million at the end so that we make sure that we're working in the same kind of units, okay? So this is going to be 25 minus 20, or 225 minus 20, excuse me, or minus 200. So this is 225 minus 200, which was equal to 25. I think that's why I put it. Plus 0.98 times 225, okay? And this is equal to 0.02 times 5, plus 0.98 times 15, right? So 15 times 15 is equal to 225, so that the square root of 225 is 15. So times 15. And we want to see what this is equal to, all right? So we do 0.98 times 15 plus 0.02 times 5. And we get that this is equal to 14.8. So his expected utility from having no insurance is equal to 14.8. And I realize that I'm a little bit over time. So if you guys need to go, you guys can definitely go. But if you are able to stay, I encourage you guys because I think this is a really good problem that will kind of, if you guys are able to solve these problems, that's great. But if you guys are stuck on these problems, then I think that this is a good problem to kind of get you guys more comfortable with that. So yeah, basically what I'm saying is 14.8 is his expected utility from having no insurance, right? And so in order to see how much he'd be willing to pay for insurance, we have to make sure that his expected utility with no insurance is equal to his expected utility with full insurance, okay? So when we do that, we do 14.8, because this is his utility, right, is equal to probability of the bad state, which is 0.02, times utility of consumption in the bad state. And we know that his utility is the square root of wealth, right? And his wealth, when he has full insurance, is M minus gamma L, right? And we also know that this is 0.98 and that his utility in the good state is the square root of wealth. So that's why we have the square root. And we know that his consumption in the good state is also M minus gamma L, okay? And so because we have like terms right here, because we have M minus gamma L and M minus gamma L, we can actually combine these two and just have this being equal to the square root of M minus gamma L. So that's something that you're always going to be able to do in these problems, is just add these two terms and have this be equal to 1. So this is like 1, if you will, right? This is 0.02 plus 0.98 being equal to 1, okay? Right, and so his willingness to pay for full insurance is going to be this amount, right? This is how much he's going to be willing to pay for full insurance. This is the premium, right? And so we want to find what this amount is, right? Because that's going to be the only unknown variable. So we have that M is equal to 225, right? So we can sub that in, right? And we want to solve for gamma L, okay? Well, first off, we know that we're going to want to square both sides. So 14.8 squared, right? So let's move this over here. We have that 225 minus gamma L is equal to 14.8 squared, right? And so gamma L is equal to 225 minus 14.8 squared, right? And I know that I'm running out of room, but I hope that you guys can see this, right? So 225 minus 14.8 squared is equal to 5.96, right? And remember, we're working in terms of millions. So our final answer is that his willingness to pay for full insurance is going to be 5.96 million, right? That's like the amount that makes him be indifferent between full insurance and no insurance, right? And so what you can kind of think of is if gamma L is any less than 5.96, then his expected utility from having full insurance is higher than the expected utility from having no insurance. And so if insurance is cheaper than this amount, then he fully insures. And if he has insurance that's more expensive than this, then he's going to have no insurance. Yeah. So gamma is just the cost of $1's worth of insurance, and L is the amounts that the amount of insurance that he buys when there's full insurance. Does that answer your question? And actually, are there any just general questions about this question and like how I go about it? I think that you're going to get a lot of these, right, when you go through your practice midterms. So I think it's really important to be comfortable with these in particular, like the willingness to pay for full insurance. But, you know, I think that every question is also just important on its own. Are there any questions about this? If there's no questions, I'm going to let you guys go. I apologize for going long, but hopefully you guys got something out of this. And if you had any questions, just know that this will get posted onto the CLES 410A GotchaSpace. All right.